Good afternoon, everyone. My name is Shungeng Zhang. I'm from Louisiana State University. Today, I will talk about DoubleFaceAD, a new Datastore driver architecture to optimize Fanout query performance. This is a joint research with Fujitsu and Georgia Tech. Fanout queries become more and more popular in real world, like data sharding and microservices. So the system bottleneck is very likely to shift from the original data store to upstream application tier. How to handle these Fanout queries in application server and always provide good services is a big challenge. There are two server designs trying to solve the above challenge. The first one is a traditional thread-based server design, which adopts one connection per thread strategy. But this design will suffer well-known multi-threading overhead when facing high concurrency workload. The second one is asynchronous, event-driven design. One reactor thread multiplexes all connections by looping over two phases, event monitoring phase and event handling phase. Asynchronous design is considered as a better choice than thread-based one because it can reduce multi-threading overhead. The challenge is that the implementation complexity of the asynchronous design. For example, the reactor thread can also employ a few worker threads just for event handling phase, which can better utilize multiple CPU cores. However, this kind of design also brings the multi-threading overhead. In the following slides, I will use a concrete experiment to show which asynchronous design is better for handling Fanout queries. This figure shows the typical three-tier topology of the web application that we use in our experiments. We compare the performance of an application server equipped with the three different MongoDB Datastore drivers communicating with the downstream data stores. There are two async MongoDB drivers, AO backend, which is the thread pool-based async, and the native backend, which is a single-threaded async. And we also study one thread-based MongoDB driver as our baseline. We use YCSV benchmark and dataset. The workload generator is JMeter. The figure shows the throughput of the server with three different MongoDB drivers when the response size is large, like 20 KB. The performance of thread-based degrades dramatically at high workload concurrency. This is because the multi-threading overhead and the native backend and AO backend still achieve high performance at high workload concurrency. The native backend achieves higher throughput than AO backend. It is because AO backend also suffers from multi-threading overhead. Due to time constraints, please refer to our paper for details. As we decrease the response size to 0.1 KB, which is small, the throughput order between AO backend and native backend has reversed. The AO backend actually achieves higher throughput than native backend. Why does this happen? Our further analysis shows it is the imbalanced workload problem in native backend when the response size is small. Native backend server employs one reactor thread in the front end to manage all connections from upstream clients, and one reactor thread in the backend to manage all connections to the downstream data stores. After receiving HTTP requests from upstream clients, the server will use the backend reactor thread to send Fanout queries to data stores and collect the results returned from data stores, which means the single reactor thread can monitor and handle all events from downstream data stores. After that, all intermediate results will be buffered and then assembled as response in the front-end reactor thread. Such a design truly reduces the multi-threading overhead. However, the lack of coordination of event processing between the front-end and the back-end reactor thread could lead to the imbalanced workload problem. First, the back-end reactor thread usually has heavier workload than the front-end due to the Fanout queries. And second, both front-end and back-end reactor thread continuously loop over two phases, even there are no pending events. Such non-stop spinning on event monitoring phase in the front-end reactor thread will lead to the spurious system calls like select, which causes the high CPU overhead and performance drop. The left figure shows the native backend achieves about 55% less throughput than AL backend when the workload concurrency is 100. Our further analysis shows that native backend has nearly 3 times of select system calls than that in AL backend. The CPU usage of the system call select in native backend is also 7% more than that in AL backend. If we go to details even further, we found that 148K out of 155K select system call are invoked in the front reactor thread, and only 7K are invoked in the backend reactor thread. Such an imbalanced workload problem causes the superior system calls in the front-end reactor thread and leads to the high CPU overhead and performance drop in native backend. Now, the question is how to avoid multi-threading overhead in AL backend and also to avoid the imbalanced workload problem in native backend. We propose a DoubleFaceAD architecture. The basic idea of DoubleFaceAD is to integrate the management of both upstream connections from clients and downstream connections from Datastore through the same reactor thread. Unlike native backend, DoubleFaceAD uses the same reactor thread, passes HTTP requests, and prepares responses for upstream clients, and also send Fanout queries and collect results from downstream data stores. In this way, DoubleFaceAD can avoid non-trivial multi-threading overhead in AL backend and also avoid imbalanced workload problem in native backend. We further introduce a Fanout query-aware priority-based scheduling algorithm to minimize the tail response time of DoubleFaceAD server. The main idea of our algorithm is to reduce the overall waiting time of client requests by first handling those Fanout queries that can assemble a complete response to a client request in the current event handling phase. For example, like the two requests with different Fanout factors in the figure. Request 1 has Fanout factor 3, and request 2 has Fanout factor 5. In the current event handling phase, request 2 can assemble a complete response because all 5 Fanout queries for request 2 are present, while only 2 out of 3 Fanout queries of request 1 are present, which means request 1 cannot assemble a complete response. The completion of request 2 will be delayed by request 1's Fanout queries. In this way, we should process Fanout query for request 2 first to reduce the waiting time. To validate the efficiency of our DoubleFaceAD architecture in terms of throughput, we use JMeter workload generator and YCSB dataset to compare the throughput of 3 servers, DoubleFaceAD, native backend, and AL backend under 2 different response sizes. The experimental results show that our DoubleFaceAD can always achieve the best performance under various workload conditions. We evaluate the algorithm using YCSB dataset and Rubel's workload generator. Rubel's simulates real-world workload traffic with a Poisson distribution. Our workload consists of 2 types of requests with Fanout factors 5 and 3. The experimental results show that our DoubleFaceAD with scheduling algorithm actually has the lowest tail response time. In conclusion, we built a high-performance asynchronous Datastore driver using an integrated design of the application server and Datastore driver. We have 3 contributions. First, we revealed unexpected performance variation of different Datastore driver architectures. Second, we pinpoint the causes of the design deficiencies in different Datastore driver architectures. Third, we designed DoubleFaceAD architecture, which outperforms all of the other asynchronous Datastore drivers. For future work, we plan to explore the feasibility of DoubleFaceAD in microservice-based environment. Thank you. Any questions?